Yeah, so I'm very glad to have this talk today and to take you on with me to the congestion situation in the Netherlands. I'm Gerben Vermeulen, a consultant at Spectral. Spectral is a software company. I tell you a bit more about it in a minute. And we work on solutions for congestion. And I'll give you some insights and some perspectives that we have experienced when trying to solve congestion. And I'm talking about congestion on power networks, of course. So that will be the main topic of today. Spectral, as a company, we specialize in system integration and the development of enterprise scale smart energy platform solutions. So we've got a lot of energy suppliers as our clients. And to help our clients best, we've got a great team, a very international team. We're based in Amsterdam with about 26 nationalities, but we're all working in the Netherlands. And there's no outsourcing, so it's all built by ourselves and also implemented ourselves. As I said, we're a software company and we have two main branches. The one is on energy systems. That will be the main topic for today. So optimizing energy systems in the broadest sense, actually. And the other part of our business is optimizing large buildings to avoid energy waste and optimize energy consumption. So we've got a lot of expertise in-house, a lot of very skilled control engineers, software developers, HVAC experts, and I myself am an expert in the energy markets data field. So that's also my background. And in my current role, I visit a lot of companies, a lot of business parks to help them out, mainly dealing with congestion. As a company, we've got quite a large presence in optimizing renewables. So currently we have about 250 sites that we optimize, where most of them are optimized on energy markets, but also more and more are optimized on the congestion markets. And congestion is a key enabler almost to install even more flexible capacity. So it's also becoming a revenue stream apart from being a hurdle, of course. So then on to the main topic of today, because I'm sure you've all heard about congestion. It's all throughout Europe, but the Netherlands is unfortunately a front runner. So as a bit of background, you see here a map of the Netherlands. This is the grid congestion map. And the left one is for export capacity, and the right one is for import capacity. As you can see, it's quite colorful. Of course, we're the country of orange, but we're turning red apparently. And we see that in, well, let's say 95% of the country, we've got limitations on both export and import of power. And that basically means that there's many renewable projects that are not happening anymore or delayed, and that there are many companies experiencing a lack of capacity from the power grid. So they can't, for example, install heat pumps to replace their gas heaters because they can't get extra electricity for the coming years. And we found ourselves in some sort of a perfect storm. But of course, we're not the only ones dealing with the grid challenges. Of course, we're moving to renewables, which are more intermittent and also growing away quicker than we expected. And as you can see here, based on this recent index, the Globsec Grid Transition Index, you see that the Netherlands is at the top of having the most amount of issues when it comes to having a grid infrastructure that is capable of delivering and transporting the needed capacity. And how come? Well, reality has exceeded our best expectations. So when looking back, like from to 2015, in the National Energy Outlook of the Netherlands, we expected to have a solar capacity installed of up to 20 gigawatts. well, with last year we already passed it. So the main congestion is on the feed-in for solar, but also wind onshore is already higher than expected. And then above that, we're of course also installing a lot of wind capacity in the North Sea, about 36 gigawatts. So that's all a big inflow, which burdens the grid more than we expected by this stage. And on the other hand, the consumption is changing and also rising, not necessarily really quickly, but it's changed a lot. So we've got a lot of data centers that came to the Netherlands because of space and cheap power, cheap cooling. We've got more and more heat pumps and electric heating, and also the electric mobility has really taken a big rise up due to a lot of incentives for electric vehicles. And when you combine that with lagging grid upgrades, well, you get the situation that we're now in. So there's a very slow ramp up of investments, and that's mainly because the distribution system operators, but also the transmission system operator TenneT, is bound to declare that they're doing the right investments for society. So they can't invest ahead of time. So that's why they're lacking. And that combines, of course, with, well, after COVID, the scarcity of personnel, the scarcity of materials, and the lagging rules and regulations to invest, to have more flexible products from the grid operators. Well, all that combined gives us the situation that we're in. Bit of a challenge for us. And we see that the coming years, this gap, you see here in Dutch, the maakbaarheidsgat, which is basically the gap between how much infrastructure can we build compared to what transport capacity do we need. So the blue line is the demanded transport capacity, and the blue field is the available transport capacity. Well, in most parts of the country, we foresee that congestion will stay for 10 to 15 years at least. So that's a pretty high burden on the economy at scale, but also on individual companies. Which means that companies are, of course, looking to what they can do. And that's actually the perspective that I want to share with you as a company that has been in the middle of these challenges and is also providing the software solutions to tackle some of these challenges. So when looking at it from an end user perspective, we basically see four pretty simple options when dealing with limited grid capacity. So say that you are a company who has plans to replace their gas heating with a heat pump. Well, you can either cancel those plans or shift them to a later point in time. You can, of course, reduce your energy consumption in other parts of the company, so optimize. That is, of course, something that every company should do. But in practice, there's still a lot to gain. You can wait for the infrastructure upgrades. But as I said, in some parts, it takes up to 10 to 15 years to have expected upgrades so that you get the capacity that you like. You can go for a collective solution, which I tell you a lot more about later. Or you can invest in an individual solution. And investing in an individual solution, I'm talking about buying a generator, renting a generator, or a battery. Well, both have drawbacks. So waiting for infrastructure upgrades is, of course, takes a long time, but investing in your own solution is quite quick. But on the other hand, capacity from the individual solution is, of course, way more expensive. So when you're investing in your own battery, of course, the capacity that is delivered through this battery is a lot more expensive than you already get from the grid operator. And cheap is relatively cheap, but it's because it's also good to know that the actual grid operator fees are among the highest in Europe by now, because of the investments that are ramping up. Companies are paying quite a lot for the grid operators' expenses at this point in time. And companies therefore can now weigh off sort of two options. They either can go for a collective solution, sharing assets, or for an individual solution where you buy your own assets. And as a software company, we are working in both fields. So we're providing energy management systems for big companies, steering the batteries and the generators. But we're also in the sort of the grid management area where we collectively steer multiple assets for multiple companies on a grid limit that these companies have together. So the whole essence of sort of we're working towards a more decentral grid situation, but we're also making it more central again. So if there were three companies, say the blue one, the green one, and the red one, and you see a power profile like you see here, they use energy sometimes at the same points of time and sometimes at other points of time. And what is happening a lot all over the Netherlands is that we're looking to add these companies up, be it physically through their infrastructure or be it virtually through an overlying software platform, and to optimize for a combination of companies instead of for each company individually. So say that these three companies have an issue with the power that they need and they want, then they would all have to buy their own smaller battery. But if you were to add them together, they would need one battery that is a bit bigger than one of three batteries, but it's way more efficient in terms of materials. It's way more efficient in terms of optimizing the capacity that is in the grid, because that's in the end what we aim for. And therefore, it's also way less expensive. But of course, there's also a pretty big challenge in having companies collaborate, build these platforms. But we see more and more of these collectives or cooperatives arising in the Netherlands where it's working, and that they are sharing capacity based on virtual or agreement with the grid operator, and that there's a software platform steering charging points, generators if needed, and batteries to stay within grid limits. So on multiple levels, we're sort of trying to optimize the capacity of the grid and to stay within the boundaries of the infrastructure that is currently in place. And when you're looking at pooling energy consumption or pooling energy connections and companies, there's basically always been one way, which is the closed distribution system. And this closed distribution system is mostly apparent, of course, in brownfield situations. So where one company would have a chain in a factory of production and delivery, with locations all being tied together. These companies had one big energy connection, and they share it on their own closed distribution loop. And these closed distribution systems are, of course, still being developed, but they are under quite high scrutiny from the authorities. And there's also quite some rules about, what can you combine? Of course, they're sort of relaxing those rules a bit, but we see that in practice, especially when there's a business park that has already been working for maybe even 100 years, that the virtual solution, that you sort of overlay a virtual layer over the physical, that is more economical and better to implement across these business parks. And in this virtual energy hub, I'll show you an example. We've got basically two options where the capacity and the energy island that provides for this needed capacity that the grid can't provide is by external financing, sort of a central energy island. And the other one is sort of business financed, where all the companies invest in a battery when they like, and that they share that battery together with their neighbors. A sort of more of a decentral, but still central in a sense of centralized business park system. And I've got a short video for you about our Schiphol Trade Park project about this sharing of capacity. To give you a bit of background, this is a large distribution center business park. So there's about 15 big distribution centers, very close to the Netherlands. And this is one of the first business parks where we have implemented this under a pilot ruling with the grid operator. And currently there's many more projects ongoing to implement this. So I'll start the video now.
Op het businesspark Schiphol Trade Park krijgen alle bedrijven een aansluiting op het elektriciteitsnet. Helaas krijgt niet iedereen meteen de gewenste elektriciteit. Als bedrijven met elektriciteit alle stroom gebruiken waarvoor ze een reservering hebben, is het onderstation volledig bezet. Nieuwe en uitbreidingsvragen moeten jaren wachten op uitbreiding van het elektriciteitsnet om stroom te krijgen. Want de netbeheerder kan hier en in steeds meer delen van Nederland niet voldoen aan de toenemende elektriciteitsvraag. Dit heet netcongestie. Bedrijven zetten nooit precies allemaal tegelijk al hun elektrische installaties aan. Ook hebben ze met het oog op eventuele toekomstige uitbreidingen een reservering voor meer stroom dan dat ze daadwerkelijk gebruiken. En omdat bedrijven ook zonnepanelen hebben, is hun stroomvraag een stuk lager. Er is daarmee nog vaak vrije ruimte op het net. Omdat centrale sturing ontbreekt, is deze vrije ruimte niet beschikbaar en bedenkt iedereen afzonderlijk een eigen oplossing. Als je niet oppast, ontstaat er een wildgroei aan gasgeneratoren met de daarbij behorende uitstoot. Dit is onwenselijk. SADC zag dat dit slimmer, goedkoper en duurzamer kon. Door op een innovatieve manier partijen te verbinden en te laten samenwerken. Samen met partners startte SADC een innovatief project voor het afstemmen van vraag en aanbod. Zodat alle bedrijven die nog geen stroomcapaciteit konden contracteren de vrije ruimte in het elektriciteitsnet wel kunnen gebruiken. Bij alle bedrijven meten we real-time hoeveel elektriciteit ze vragen. Deze informatie verzamelen en analyseren we in de control room. Alleen wanneer de totale energievraag te hoog wordt, wordt bij één of meerdere bedrijven de accu met opgeslagen duurzame energie ingezet. Of, als het echt niet anders kan, de gasgenerator. Zo komt de totale elektriciteitsvraag niet boven het niveau dat het elektriciteitsstation aan kan en is de betrouwbaarheid van het net gewaarborgd. Op deze manier krijgen alle bedrijven toch de elektriciteit die ze nodig hebben, bespaart iedereen geld en vermijden we onnodige uitstoot van CO2. Met deze oplossing geven we elkaar positieve energie.
Yeah, so this video is in collaboration with SADC, which was the developer of the business park, and we are the technology provider for this virtual grid solution. So here you've seen an example of multiple assets in this business park which are being optimized to cater for the whole area. So in this specific project, there's 2 generators and 3 batteries. And the companies are paying to loan capacity from the other company when they need it and don't have it themselves. So there's also a whole financial settling system behind this. Because companies, in essence, sort of pay for getting power from the grid operator, and they also pay for getting power from the battery of the neighbor. And this is sort of decentral assets in this central virtual energy grid. But currently, we also see other, let's go to the next. We see another option as well, where there's another company, a partner of ours, Jules, who is sort of providing a central energy island for capacity. So the difference is that you're not placing gas generators or batteries at a couple of companies, but you're centralizing this whole system where all these companies pay for the capacity that was delivered by the energy island from the externally financed energy island. And in that sense, this differs from the solution I just showed you, because companies here don't have to invest in these assets themselves, but they pay the energy island for the added capacity that would not be available from the grid. So you basically sort of pay one grid operator the normal fees for the grid that is already there, and you pay the energy island for the additional capacity that has been delivered to you. So this is also one perspective that is now being implemented across the Netherlands. But the main one across all the 1,200 business parks, which are suitable for these kind of solutions, is the virtual one where companies can invest in their own solution. Because probably, as you expect, Some companies have an issue right now, want to invest in battery, and later on share it. And just to wrap it up, we see a couple of steps and requirements for realization of these collectives of capacity. And I'm also very curious if these collectives are already something that is happening in your view in other countries besides the Netherlands as well. Well, there's a couple of steps to realize this. The main thing is that it's about products and regulations from the grid operator and the authorities. This project at Schiphol Trade Park I just showed you started 4 years ago, and there's only 2 that have followed, and only right now we're doing like 30 projects, but it's still ramping up, just all to maximize use of the available grid. So that's it. Thanks for listening, and we can take some questions. I think I'm still within time.
Yes, many thanks. I think you are perfectly in time. Yes, I think this gave a very nice overview on what you're doing, and also a little bit of a Dutch lesson.
Yeah, video, yeah.
Nice to hear as well.
Yeah.
Okay, so I am not sure, do we have a question from the audience? Feel free to ask. Yes, Christoph, please.
Hi, can you hear me?
Yeah.
Yeah, thank you very much for the presentation. I'm interested in, I'm not sure if I got it correctly. So in both examples that you showed us, you rely on the existing infrastructure from the grid operator, and the grid operator is continuing to operate its grid to perform his role.
Yeah.
Right?
Yeah, correct. So we add a virtual layer on top of it. Of course, you also can build a complete island, but that's way more expensive. So in essence, what we now see is when a business park and multiple companies there don't have enough capacity, they will still use the capacity that they've already got and wait for 10 years to get the added capacity. But in the meanwhile, we sort of implement this virtual layer and some assets to cater for the extra need that they have. So it'll be on top of what they currently have, which is also crucial because, of course, the added capacity through these assets is more expensive than the capacity that you pay for to get from the grid operator.
Okay, thanks.
Okay, then we have Esther was the next one.
I wanted to know, do you think that the infrastructure actually will expand as planned, or because you build these not island solutions, but still more local ones, that infrastructure projects are also stopped?
I don't expect that these infrastructure projects will be stopped. These infrastructure investment projects are sort of still prioritized based on the need and the societal value of investing in specific locations. Currently, it's more of a bandage to stop the bleeding than it is the actual cure for the disease, I'd say.
Okay.
But what is a great upside of implementing such a software platform, like in the middle, to optimize for capacity, is also that you have a system in place that you can use to optimize for local energy consumption and use the batteries eventually not for providing capacity, but to store the solar energy or to be working on the energy markets. So it's more of an upside and an add-on than I would say that it would replace the need for an investment.
Okay.
But it will dim it down, I guess. Yeah.
Okay, thanks. Then we have one question from Martínez.
Hi, thanks for the presentation. It was very informative. I have 2 main questions. One is you mentioned cost, like the relative cost between this kind of solution and implementing something from the grid operator. I'm wondering if you could give any numbers that, like, what's the typical grid fee or per kilowatt hour, per kilowatt versus doing something like this? And the second question was the regulatory side, because I imagine that the grid operators want to have pretty good insight of what's going on inside there, and how do you kind of get them to agree on implementing something like that?
Yeah, sure. Yeah, so we're not the guys selling the hardware, of course, but from our partners, I hear that capacity cost, so for the kilowatt delivered, you pay about 4 times as much as from the grid operator. So that's in the case where the joules island is in the middle, and that's the added capacity. And of course, it's only a smaller amount of what is being delivered. Often companies get 500 kilowatts through the grid operator and an additional 100 through such a solution, but it is a lot more expensive indeed. So that's question one. And the second question on how do you deal with the grid operator. So in that example of the Schiphol Trade Park project, the grid operator is closely involved. It's an innovation project for them as well. And there's several mitigations implemented to, of course, tackle the most crucial elements. So there's also sort of a stop sign built into the stop station, where the grid operator measures themselves whether we are delivering what we say we deliver through the software platform, and that is a security to them that it's of course all correct to do such a thing. And when looking forward to all the other upcoming projects, the grid operators are all doing pilots, so they're all also trying to figure out what are our minimum requirements in terms of response, security, redundancy, and that is ongoing.
Okay, many thanks. Yeah, considering the time, I would say we can move on. If there would be some extra questions, maybe the people can write it in the chat or to you directly. So then maybe later on there is time.
Sure. Yeah.
Perfect. Thank you again for the talk. So Miguel, we can move over to you. You can share your screen.
Yes, I'm going to share my screen. Sorry. Second. You can see my screen, right?
Yes, perfect.
Okay, perfect. So, well, first of all, thank you, Stephanie, for having me over in this session. I think it lines up very well with what Gerben has already presented, because he's been speaking about more of what, for example, large consumers can do with batteries. I'm going to look a bit more into the distribution grid operator side and how we can take all this flexibility from batteries that are distributed and to improve the cost effectiveness and the reliability of our power distribution systems. And this has been part of my PhD thesis, but also from other projects that we have been running at our institute. So first, I will start with why we need flexibility in our power systems, and then I will go into how value stacking can improve the competitiveness of energy storage, because it can provide many different services to the grid. And I will present two case studies that we have done in collaboration with Spanish DSOs, where we have analyzed if we can defer some distribution grid investments with batteries and if we can improve the reliability of distribution grids. And I will wrap up this session with some conclusions. So first is why we need batteries in the power system. No? So as Gerben has already presented, the power system is experiencing a transition where we are integrating more intermittent renewables. We are also electrifying our economy, and that poses new challenges to our power systems. And one key aspect is that this is introducing a lot of uncertainties, and we need to adapt to these new situations. And flexibility, it's a word that is very trendy right now in power systems, but I would like to keep it to the original definition, which is the ability to change or be changed easily according to the situation. And this is something that energy storage and among the energy storage solutions that we have, batteries, are a crucial technology to provide this flexibility in the power system. And here we are talking about very different time domains and scales. So for example, we can have system-wide problematics like stability of the power system. So we have a reduction in the frequency and we need to balance it. Again, that's maybe a short time, but we also need to care about long-term adequacy of our power system. So if we have enough firm capacity. And we have also very local issues, for example, congestion management and voltage control. Then batteries can get revenues from very different sources. The two most common ones, especially in Europe, are energy arbitrage from wholesale electricity markets, where we can sell electricity at times with high prices, and then recharge our batteries at times with low prices. But then we also have different markets where we can provide services to the power system. Some of the most common ones are the ones related to frequency containment and restoration. And here I provide a short figure where we have different of these reserves that we are activating, from primary to secondary to tertiary reserves. And then batteries can participate in these markets. And usually these are well-established markets, and there is a question of how batteries can participate and what revenues they are going to get from them. But then there are many other applications that are emerging and that have been less studied in the literature, that go from improving the integration of renewables, peak shaving, increasing firm capacity reserves, and lastly, we have more local issues, which are the ones that have been given less attention and that I will be focusing on this presentation, especially on power outage mitigation. So how can we improve reliability indices and maybe substitute some of the backup diesel units that we are using at the moment? And then in transmission and distribution investment deferral, we can use batteries as non-wire alternatives to reduce congestion and voltage limit violations. So first I will start with the case study on distribution grid investment deferral. And one of the ideas or the reasons that we were asking ourselves this question was that, for example, the European Commission recommended all system operators in Europe to check if batteries could be a cost-effective non-wire alternative to conventional reinforcement, so building, for example, new lines or transformers. And this is an important topic because at the moment, DSOs in Europe cannot own, develop, manage, or operate batteries unless they are fully integrated network components, meaning that they cannot be used to buy or sell energy in electricity markets, and they need to receive approval from the national regulatory authority. And since this is a question that has not been really studied, one of the main things is, okay, when is the installation of DSO-owned batteries in distribution grids a techno-economic solution? And especially if we consider different load growth scenarios. And the idea of studying these DSO-owned batteries is to only look at the value of the battery on the power system, because many studies, they consider the combination of markets, for example, so revenues from energy arbitrage with these services, and that distorts the optimal investment decision. So we are not, so maybe you're doing an investment for the market and you are not considering the value on the distribution grid. So one of the things we also were asking ourselves, what is the portion of the costs of the battery that we can recoup through these improvements on the grid, and then evaluate the potential of some novel approaches that I will cover later. So what we did was to take in a Spanish medium voltage grid. We tried to optimally size and site a battery within this grid. We considered a future scenario where the demand was exceeding by a little bit the capacity of the substation, and the optimal solution was to install a battery at the end of one of the feeders. Then this is just a screenshot, but then the question is, for how many years are we going to defer this investment, and does it make sense overall in the lifetime cost of the battery? So here I have a figure where I can see for different load growth rates, So how much the load is increasing from one year to another. And we can see that the battery installation is only cost efficient for very small load growth rates. So it is a very specific condition when the load of the power system would stay slightly higher than the capacity of the substation, that it would make sense from an economic perspective. No? And we can see that we would need to at least defer the reinforcement for 5 years to invest in this battery. So then the question is, okay, is this all we can do? Or, I mean, could there be other options for batteries to be installed? The first thing we thought about was mobile batteries. So I can have a battery maybe in this grid and then move it to another place when I don't need it anymore because it's not enough to defer the reinforcement. Here I provide a figure where the top part, where you see 16 years of project duration, that would be the original graph I presented in the previous slide. And here the project duration is the number of years that the battery stays at that location. So if we reduce the project duration, it means that we are moving the battery more along its lifetime to other grids. What we can see is that although we increase the utilization hours of the battery, this has an additional cost because we need to transport the battery to other locations and install the battery at other locations. Since this is an emerging topic, there are high uncertainty on the data for these costs, and that's why we don't see a large increase. So here I have put in gray all the area where it wouldn't be economically viable, and we can see that even if we move the battery a lot, maybe every 4 years, we are not really increasing this window when it's interesting. This might change in the future as maybe we have new developments in technology or more projects that have tried to do work with mobile batteries. And then the second option was, okay, we can stack maybe revenues. So I might be using the battery to defer the grid investments, but we can also use the battery for other applications. So how much of the battery, of the cost of the battery, can I recoup through these specific applications on deferring the grid investment? Here on the figure on the right, we can see that we are recovering at least 25% of the cost of the battery for all of the load situations, all the different scenarios that we have considered. Considering that we are only using 10% of the battery cycles because these peak conditions where we have congestion or voltage issues only happen a few days per year and a few hours per year, then we can say that the percentage of the battery cost that we are recovering through a deferral of grid reinforcements is higher than the number of cycles we are using, which means that it has some value. The problem is that if we are dedicating the battery to just this application, we are not utilizing all of the cycles of the battery. So the recommendations would be first for DSOs, if they want to make an investment on an integrated network component, they need other benefits. We are going to see later what happens with reliability. And if it's a third-party owned storage, so if we have a battery that is already installed at that location, the DSO could procure a flexibility service. So ask this third party to manage their battery according to a given signal to adapt to the situation of the grid. So if we foresee that there is going to be congestion, we can ask the battery to discharge some power to relieve this congestion. And this is an emerging topic especially in Europe, where we expect to have new markets for local flexibility markets with the upcoming network code on demand response. Then I will move to the second case study where we have considered how we can improve reliability of the distribution grid. So first, reliability of the distribution grid is what allows the grid to withstand sudden disturbances that can lead to power outages. So I might have a fault, for example, that can lead to an outage. And since the grid is usually radial or almost radial, some of the consumers are going to lose their supply. So many DSOs, they have incentive or penalty schemes to maintain a certain quality or continuity of supply indices. For example, in this application, we consider SAIDI as one of these reliability indices. And then the DSO have different alternatives to improve reliability or to maintain the objectives that are set by the regulation. Conventional investments are usually the installation of switching and more control equipment, meshing existing feeders so that we can reconfigure the grid, and maybe if we have a failure at one of the feeders, we can connect their consumers and supply them from another route. And our objective in this study was to improve the reliability through microgrids with batteries and or PV systems. So we can isolate a part of the grid, keeping their supplies with the battery. And we have done a case study for a rural Spanish medium voltage grid, which was fairly large with almost 3,000 supply points. And on the figure of the right, you can see that through the existing switching equipment, we could divide this grid into 4 areas. And then we could connect these areas to form microgrids. And if we have a storage or other distributed energy resources, we can maintain the power supply after a fault. And the results for this case study, what they show is that if we only have batteries, out of all the Pareto optimal solutions that we achieved, but the solution that only relied on batteries provided the lowest reduction of SAIDI. Here, having a reduction of this index is good because it has to do with the number of hours that we are losing, let's say, the supply of interrupting the supply. And most of these solutions relied only on diesel units. So here we had different options ranging from batteries to PV systems to diesel units and their combination. And the third result was that investing only in dedicated solar didn't make sense for this. I mean, you're not going to install generation just in case you have a failure. So we would have to rely on the solar capacity that was already in these residential households, for example. And here we did, my colleagues, they did a similar study to what I did in the previous case study. So considering that what would happen if the costs of the battery were reduced. And we can see that if the cost of the batteries are reduced by 80%, then they would become more competitive than diesel units. And again, the way we can read this result is that we might not expect such a high reduction on the cost of batteries in the future, but we can consider that we would be able to recoup at least 20% of the battery cost from providing this service that would enhance the reliability of the distribution system. And considering that we have very few outages per year, here it would be an average of 4 to 5. That means that has a lot of value because we are using a few cycles of the battery to recoup 20% of our costs. So to conclude, what we can see is that dedicated batteries for a specific grid application are generally not an economically viable alternative. However, the percentage of the cost of the battery that we are recovering through both of these services would be deferring grid reinforcements and also improving reliability indices are higher than the percentage of the cycles used, meaning that there is value on these applications if we can stack revenues, for example, from these different system services. So we could participate, for example, in markets for balancing the grid, providing, for example, secondary reserve. We could have other adequacy services, for example, in capacity, in future capacity markets. And then that would make sense and allow us to invest on batteries and maybe improve the profitability of batteries. And here I would like to end with a few questions that we need to ask ourselves, because as you have seen, all of this battery adoption is changing how we operate and think about distribution grids. And one of the things is that how much storage we need distributed. So, for example, in Spain, we have pumped hydro, which is a very centralized storage, but we have seen if we have some batteries that are distributed or located in medium or low voltage grids, they can improve our grids, and that has a benefit overall for the power system and for the energy and for enabling the energy transition. Then the second question is what incentives and mechanisms should be introduced? Because right now, if you have a battery and try to provide something for the grid in many countries, there is no incentive for that, so no one is going to do it. Some examples can be in the Netherlands, they have some congestion management. In the UK, they have local flexibility markets, but many countries don't have any incentives. And also for the DSOs, because if they are not remunerated, they are not going to use this flexibility from batteries. And lastly, the last question would be how distributed batteries would compare to other alternatives. Because, for example, for congestion management, we can use demand response also, and that would provide a similar effect. And here I have considered only the value of the batteries, but we would have some competing technologies, and we need to see which would be the best solution. So thank you for attending this presentation. If you have any questions, I think we still have some time, and I have included here for further reading these papers if someone is interested in reading them.
Perfect. Yeah, many thanks, Miguel, for your presentation. It really shows that there was a lot of detail and work going into your PhD thesis, if I understood it right. And
yes, especially the first part, it was most closely related to my thesis.
okay.
Yes.
Yeah, very nice. Thanks. Do we have? Yeah, we have a question from Axel, please.
Yeah. In the makeup of the battery energy storage cost, is it more sensitive to the cost of the cells or the cost of all the surrounding things like the inverters and the discharge duration? What really makes it up there? Would it be cheaper if we make larger, longer discharging batteries, or are we talking like 1C batteries?
Yes, I'm not an expert on that side, but the cost of the batteries, like the cells itself, it's a huge part. It's a very important part of it. It could be around maybe like 50% of the total cost, and is the part where we are foreseeing the highest reduction. That would be for a normal battery application. If we are considering mobile batteries, the installation and shipping costs and transportation, that could be reduced if we start to build dedicated batteries that we are considering that they are going to be moved. And maybe also we are going to have a learning curve on using these systems. But yes, the cells are a very important part of this.
But would longer batteries of discharge over longer durations have that capability be more useful for what's called reducing grid congestion and so on?
Yes, here, let's say the number of hours or the relation between the power and energy, that has to do a lot with the specific situation on your grid. For example, in the case for deferring investments on the grid and to resolving the congestion at the substation, we had a peak that lasted for 3 hours. If you have a battery that has less, it wouldn't be useful for this application. If you have more hours, it would probably be not used. So we consider here a 4-hour battery for this application, which is a common number also, for example, for residential batteries. And that's more or less aligned with that.
Thank you so much. It was a very nice presentation.
Thank you.
I've got not necessarily a question, but also some info. So in the Netherlands, around the city of Utrecht, which is in the middle of the Netherlands, there's a really pressing need for capacity. And the local distribution system operator has actually sort of put out flex tenders where private companies will place generators next to their substation, where the DSO will pay for the capacity that is delivered, but not for the device itself. Where those generators will be used for a maximum of, I guess, 800 hours. So it's in practice, there's not batteries yet at the DSO level because of the storage and the trading of energy, which is also hampering it. But generators are being placed soon.
Yes, I mean, what we see is, for example, that this type of signals, what they can make is if, for example, I'm a promoter, I'm looking for a place to install a battery. If I know that in a certain area there's going to be some sort of congestion and might have some incentives or potential revenues for participating in this type of markets, it's going to incentivize maybe these promoters to select these locations and maybe increase their profitability. So it could lead to more batteries or more distributed energy resources in the long term.
I think there's two things happening. So you've got the commercial projects that are also acting to resolve congestion. Those are like everywhere right now.
Yes.
And on the other hand, the one I was talking about is just specifically for congestion.
Yes, I think here this part is more on considering that I mean that we are going to need some investments in the future. So what happens if we have limitations? For example, there is a lot of value, and I think that your talk, Gerben, was a really good starting point to see why we need that.
Yeah, very insightful. Thanks.